MPLS-SR MPLS segment routing, MPLS-SR, often simply called segment routing, SR, represents the most significant evolution in MPLS technology in the last 2 decades. It was designed to simplify the network by removing the need for complex middleman protocols like LDP and RSVPTE, making the network more programmable and ready for 5G. In a nutshell, segment routing moves the intelligence from the core of the network to the source, the ingress router. The core concept, source routing in traditional MPLS, the network core manages the paths. In segment routing, the source defines the path. The analogy, think of traditional MPLS as a traveler following a series of signs at every intersection. In segment routing, the traveler is given a list of GPS coordinates, segments, before they leave. The traveler doesn't need to look at signs anymore, they just follow the list. The segments, a segment is an instruction. It can tell the packet to go to node A or go out via interface 5. These instructions are stacked in the MPLS label stack. Key components, SIDS, segment identifiers, in an MPLS-SR network, labels are replaced, or rather, mapped, to SIDS. Point 4. There are 2 primary types, a prefix SID, node SID, what it is, a unique identifier for a specific router, node, in the network. Scope, it is global. Every router in the network knows that SID 100 means router A function, it tells the network to send the packet to that node via the shortest path. B. Adjacency SID, adjective SID, what it is, a local identifier for a specific physical link between 2 routers. Scope, it is local. Only the router that owns the link knows what it means. Function, it forces a packet to use a specific exit door, interface, regardless of what the shortest path says. How MPLS-SR works. Segment routing leverages existing IP routing protocols, like OSPF or ISAs, to distribute labels. 1. Eliminating protocols, it removes the need for LDP, label distribution protocol. The SIDS are advertised directly inside the OSPF/ISAs packets. 2. Path steering, to create a specific path, the ingress router pushes a stack of labels. Top label, go to router B. Middle label, then take the specific link to router C. Bottom label, then go to the final destination. 3. Stateless core, the core routers, LSRs, do not need to maintain any path state. They just look at the top label, follow the instruction, and pop it. Advantages of MPLS-SR simplicity, by removing LDP and RSVPTE, the network has fewer protocols to manage, fewer handshakes, and is less likely to crash. Scalability, since core routers don't store path information, the network can support millions of unique paths, LSPs, without running out of memory. TILFA, topology independent loop-free alternate. This is SR's superpower. It provides 50 milliseconds protection in any network topology, even complex ones where standard MPLS would fail to find a backup path. SDN ready, it is perfect for software-defined networking. A central PCE, path computation element, can tell a router, use this stack of labels to avoid the congested link, and the router can do it instantly. Comparison, traditional MPLS versus MPLS-SR feature. Traditional MPLS, LDP/RSVP, MPLS-SR, segment routing, label distribution. LDP or RSVP IGP, OSPF/ISAs, path state stored in every router on the path only stored at the source configuration. Complex hop-by-hop. Simple source-based protection. Fast reroute. Complex, TILFA, simpler and better, network load high, constant signaling, very low. MPLS-SR label stack. Example. In an MPLS-SR, segment routing, environment, the label stack acts as a list of instructions or a roadmap provided by the ingress router. As the packet traverses the network, the routers follow these instructions by looking at the top label, executing the move, and then popping it to reveal the next step. Here is how a packet would be forwarded using the segment lists SID3, SID2, and SID1, from top to bottom. 1. The anatomy of the stack. In this example, the ingress router, the source, has calculated a specific path that is not necessarily the shortest one. It pushes 3 labels onto the IP packet, top label, SID3 the immediate objective, example go to node 3, middle label, SID2 the intermediate objective, example then take this specific link to node 2, bottom label, SID1 the final objective, example deliver to node 1/egress. 2. The packet journey, hop by hop, step A, at the ingress router, source, the router receives a standard IP packet. Based on its policy, or instructions from an SDN controller, it realizes this packet needs a custom path. Action, it pushes the stack 3, 2, 1 onto the packet. Forwarding, it looks at the top label, SID3, and sends the packet toward the shortest path to reach node 3. Step B, reaching node 3, the first instruction, as the packet travels, intermediate routers, LSRs, only look at the top label, SID3, and perform standard MPLS swapping or forwarding. When the packet arrives at node 3, action, node 3 sees that it is the owner of SID 3. It pops SID 3. Result, the stack now has SID 2 on top. Forwarding, node 3 now looks at the new top label, SID 2, and follows its instruction. Step C, executing the SID 2 instruction. If SID 2 is an adjacency SID, representing a specific physical link, node 3 will ignore the shortest path to the destination and force the packet out of that specific interface. Action, node 3 pops SID 2 as the packet crosses that specific link. Result, the stack now only contains SID 1, the bottom of stack bit is now set. Step D, reaching the final destination, SID 1, the packet arrives at the final destination or the egress LER identified by SID 1. Action, the router pops SID 1. Result, the MPLS header is completely removed, revealing the original IP packet. Forwarding, the packet is sent to the final customer site or application. 3. Comparison of stack changes. Location label stack, top to bottom, active instruction at ingress 3, 2, 1. Follow shortest path to node 3 arriving at node 3, 3, 2, 1. Node 3 recognizes itself, pop SID 3 leaving node 3, 2, 1. Use specific adjacency / link for SID 2 arriving at egress 1. Egress recognizes itself, pop SID 1. Final delivery none / IP deliver original IP data. 4. Key advantages of this example. 1. Stateless core. Notice that the routers between the source and node 3 did not need to know the whole path. They only needed to know how to get to SID 3. 2. Explicit path. By including SID 2, likely an adjacency SID, the source forced the packet to take a specific link that might be less congested, even if the shortest path math said otherwise. 3. Low overhead. The core routers don't need to store path 3-2-1 in their memory. They just process the labels they see in real time. MPLS-SR takes the best part of MPLS, the fast label switching, and combines it with the simplicity of the IGP, Interior Gateway Protocol. It is the foundational technology for 5G network slicing, allowing operators to create thousands of virtual networks over the same physical hardware with zero overhead in the core. Advantages of MPLS-SR. MPLS segment routing. MPLS-SR is widely considered the holy grail of modern networking because it solves the complexity issues that plagued traditional MPLS for decades. By moving the state from the network core to the packet header, it transforms the architecture into a programmable, software-defined system. Here is a breakdown of its key advantages. 1. Simplified control plane. Traditional MPLS requires a mesh of protocols to work, OSPF/IS for routing, LDP for basic labels, and RSVPTE for traffic engineering. This creates a massive amount of background chatter. Protocol elimination. MPLS-SR completely removes the need for LDP and RSVPTE. IGP extensions. Label information is carried directly inside existing routing protocols, OSPF or IS. Benefit. Fewer protocols mean fewer software bugs, faster boot times for routers, and a significantly smaller attack surface for security. 2. Granular traffic engineering, SRTE. In traditional networks, traffic engineering, TE, was a heavyweight task that required core routers to keep track of every single tunnel. Explicit paths. With SR, the ingress router can dictate the exact path a packet takes simply by stacking labels. It can force a packet to avoid a specific high latency link or prefer a specific high bandwidth one. No path state in the core routers, LSRs, don't need to know the packet's ultimate destination or its complex path, they only process the top label in the stack. 3. Massive scalability. In traditional MPLS, every core router has to store state information for every tunnel passing through it. 5. As the network grows to thousands of routers and millions of tunnels, the core routers eventually run out of memory, the state explosion problem. Stateless core. Because the path instructions are in the packet header, the label stack, core routers store zero information about individual tunnels. Capacity. This allows the network to scale to the size of massive global hyperscale data centers and 5G networks with millions of individual slices. 4. TILFA, the super fast reroute. Standard MPLS fast reroute, FRR, is notoriously difficult to configure and often fails in complex network topologies, like square or ring shapes. Topology independent loop-free alternate, TILFA. This is a native feature of segment routing 6. It allows the network to calculate a backup path for 100% of the network topology. 50 milliseconds recovery. If a link fails, the router immediately applies a repair label stack to the packet. Because the backup path is pre-calculated by the IGP, the recovery happens in under 50 milliseconds, ensuring zero interruption for voice calls or video streams. 5. Flexible path steering. Modern networks need to be application aware. For example, a banking app needs low latency, while a video download just needs high throughput. On-demand next hop. Through an SDN controller, like a PCE, the network can dynamically change the path of a specific traffic flow in real time. Complex steering. You can create a segment list that says, go to node A, then pass through this firewall. Service chaining. then exit through node B. All of this is done by simply changing the labels at the ingress router, without touching the configuration of any other router in the network. Summary table: MPLS versus MPLS-SR feature. Traditional MPLS-MPLS-SR protocols IGP plus LDP plus RSVP IGP only, OSPF/ISAs, core router load high, stores all tunnel info, 0, stateless, path decisions distributed/complex source-based, ingress, protection limited FRR 100% TILFA coverage programming difficult, hop by hop, easy, label stacking. Applications of MPLS-SR. MPLS segment routing, MPLS-SR, has rapidly become the preferred architecture for high-scale, programmable networks. By removing the complexity of legacy signaling protocols, it has enabled new use cases that were previously too difficult or resource-intensive to manage. Here is where MPLS-SR is being applied today. 1. Global backbone networks. Tier 1 internet service providers, ISPs, and global carriers use MPLS-SR to manage massive amounts of traffic across continents. The application: moving petabytes of data between major exchange points. Why SR? Traditional RSVP traffic engineering required core routers to maintain state for every tunnel. In a global backbone with millions of flows, this led to memory exhaustion. MPLS-SR is stateless in the core. The routers only need to know the next segment, allowing the backbone to scale infinitely. 2. Data center interconnect, DCI. Hyperscale cloud providers, like Google and Meta, use segment routing to link their massive data centers. The application: steering traffic between data centers based on application needs, example prioritizing database replication over background backups. Why SR? It integrates perfectly with SDN, software-defined networking. A centralized controller can look at the entire global network and push a label stack to the ingress router to steer traffic around a fiber cut or a congested peering point in real time. 3. 5G transport networks, network slicing. 5G is the biggest driver for MPLS-SR adoption. The application: network slicing. 5G requires the physical network to be carved into multiple virtual networks with different characteristics. Why SR? SR allows the operator to create a slice for autonomous vehicles, ultra-low latency, by forcing those packets through the shortest physical path, while a slice for 4K video streaming, high bandwidth, can be steered over a longer path with more capacity. This is all done using different SID stacks for each slice. 4. Segment routing VPNs, SR VPN. MPLS-SR enhances the traditional VPN model, L3 VPN and EVPN, by making the transport layer much simpler. The application: connecting corporate offices or providing private cloud access. Why SR? In traditional VPNs, you needed LDP to distribute labels for the transport and BGP for the VPN. With SR VPN, you use BGP for the VPN services and the native IGP, OSPF/ISAs, for transport. This reduces the number of protocols the router has to run, making the VPN more stable and easier to troubleshoot. 5. Advanced reliability, TILFA. Fast reroute, FRR, is the ability of a network to recover from a failure in under 50 milliseconds. The application: ensuring that high-definition video calls or financial trades are not dropped if a fiber cable is cut. The breakthrough: TILFA. Traditional MPLS-FRR was limited by topology. It couldn't always find a backup path in complex ring or square fiber layouts. Topology-independent loop-free alternate, TILFA, is a native feature of SR that guarantees a 50 milliseconds backup path for 100% of the network. It does this by pre-calculating a repair SID stack that is applied the instant a link goes down. Summary of application advantages. Use case: legacy limitation. MPLS-SR solution: backbone state explosion, memory, stateless core, header-based, data center rigid, manual paths. SDN programmability. 5G transport: one-size-fits-all granular slicing via SIDS VPNs. Protocol: spaghetti, LDP/RSVP, IGP only transport. Fast reroute. Partial coverage, 50 to 80%. 100% coverage, TILFA. Comparison of the technologies we've discussed. Technology best for: key superpower, DWDM, raw capacity, multiple colors of light on one fiber. OTN, fiber management, the digital wrapper with error correction, FEC. MPLS-TP, absolute reliability, deterministic, static paths for 50 milliseconds transport. MPLS-SR, modern scalability, source routing, perfect for 5G and SDN.